This is a screencast of a folder of a problem involving friction with a diamond that's resting on a book. Okay, so a 0.5 kilogram diamond, it's a big diamond, rests on a 1.5 kilogram book, and that rests on a frictionless surface. The book is then pushed with a horizontal force of 10 newtons. What is the acceleration of the book diamond system, assuming the diamond stays on the book? Well, here is a sketch of what's going on. A force applied to the book with a diamond on it, frictionless, so mu equals 0. Here's a list of values over here. Here's a free body diagram of the system. I want the acceleration of the system, so I draw a free body diagram of the system. There's a gravitational force down, normal force up, and the applied force of 10 newtons to the right. The acceleration is all in the x direction, so that comes from the combination of forces acting on the mass of the system. There's only one force that is in the net force. I guess it's fair to say that F, the applied force, is the same as the net force, since the normal and gravitational forces cancel, divided by the mass of the system. So that's 10 newtons divided by 2 kilograms, 5 meters per second squared. The next part asks, what is the net force on the diamond? Well, I can start with the equation that the acceleration of the diamond comes from the net force on the diamond divided by the mass of the diamond. So the net force of the diamond is equal to its mass times its acceleration. The mass of the diamond is 0.5 kilograms times 5 meters per second squared, so 2.5 newtons is the net force on the diamond. Next, it says to draw a free body diagram of the diamond and indicate the direction of the diamond's acceleration. Well, we know from this picture that if the diamond stays on the book, the diamond will accelerate to the right. So the direction of acceleration is to the right. Now check out the free body diagram. The diamond has gravitational force down, normal force up, a friction force to the right. Well, that's surprising. Usually we imagine friction force to oppose the acceleration, oppose the motion of something. But here, it is the friction of the diamond on the book that allows acceleration to occur. If there were no friction, then the book would just slide right under the diamond, and the diamond wouldn't accelerate. There's no arrow to the left balancing out friction. Friction is a force to the right that gives rise to the diamond's acceleration to the right. What is the minimum coefficient of static friction that must exist between the book and the diamond? Well, as we said, the net force on the diamond is 2.5 newtons, and the net force on the diamond is the force in the x direction. That is the frictional force. If we're talking about the minimum coefficient of static friction, that means that we want the coefficient of friction to be as low as possible to still give this amount of friction, 2.5 newtons on the diamond. If we have the minimum possible coefficient of static friction, that's like saying this 2.5 newtons of friction on the diamond is the maximum amount of friction that the book can provide. So it's like saying that the force of friction on the diamond is like the maximum static friction force. The maximum static friction force is the coefficient of friction times the amount of normal force, and that's equal, in this case, to 2.5 newtons. So dividing both sides by the normal force, the coefficient of friction is equal to 2.5 newtons divided by the normal force. For the diamond, the normal force on the diamond is balanced by the gravitational force on the diamond. So that's 2.5 newtons over the gravitational force on the diamond is 5 newtons, so the coefficient of friction is 0.5.